Welcome in part 3 of radiation effects on CMOS imager. I'm Jérôme Pratlong, Chief Engineer at Teledyne E2V, specialized in visible and infrared detector for space application. In the two first videos, we looked at total ionization dose and displacement damage dose. Today, we will look at single event effect, also known as heavy ion radiation. This type of radiation affect the performance availability and define the end-of-life operability of a detector. At the opposite of the two first type of radiation, this one is mainly a concern for the periphery and not for the pixel. In this video, we will look at the basic mechanism, the main impact on imager, and we will give some takeaway from our detector silicon results. The interaction of ion with the material creates an ionization track by direct ionization. It is the Coulomb scattering. The main effect on imager is the buildup of charge at the drain and source transistor, and that can cause three types of non-destructive effects: SET, single event transient; SEU, single event upset; and CFE, single event functional interrupt. But it can also create a more destructive effect that is known as latch-up. The test is biased and clocked. The LED is above 67.5 MeV in general, but can be up to 80 MeV. The three non-destructive effects are single event upset, SEU, where the logic state of a memory element is affected. The single event transient, that's more concerned with clock data propagation, and that can cause an erroneous data capture. Single event functional interrupt, CFE, is a temporary loss of device functionality. The destructive possibility is what we call single event latch-up, and that is caused by parasitic thyristor within the silicon that are tricked and can cause catastrophic failure. This radiation affects mainly the digital logic, and this buildup of voltages at drain or source of a transistor can then turn off and on a transistor. If there is a series of inverter, this buildup of voltage at one node can be reshaped and transformed into a proper pulse that, when brought to a memory element, like a flip-flop, it can create an erroneous capture of data within the memory element. It is also possible that this voltage is created within the memory element, and via the positive feedback in the memory element, then this transient will be captured as a solid logic level, 1 or 0. The modeling approach to design such structure is to take into account the process, the design, but also ion characteristics. This was used via a Musca tool in order to generate stimuli in the shape of current source applied in various parts of the design. This can be done via cadence and can be simulated electrically, giving the weak point and strong point of the structure for optimization. The single event latch-up is the fact that a charge generated inside the silicon will trigger a thyristor network formed between an N-type transistor and a P-type transistor. There is a positive feedback loop that will apply a great gain on this current, leading to potentially a very high current demand between a supply and the ground, basically creating a short. By doing so, this could be much higher than what the electron migration rules can tolerate within the silicon. And some power supply can be completely broken from the external world, making the device unusable. This is a typical representation of a post-radiation test, which is the single event latch-up cross-section per device, with in x-axis the lead at which it was tested. This is an example of a non-radar off-the-shelf device. As the LET become larger, therefore more energy deposited, more electron released through ionization. That means a larger current pulse is created, and that leads to more and more possibility to have a positive thyristor latching. That's what we see as the curve increase with the LED. Below a certain threshold, the current pulse is too low, small, to switch on the thyristor, and no latch-up events can be observed. Therefore, what we see below the first point, around 2 or 3 MeV. Therefore, we can see that with a non-radar off-the-shelf device, the cross-section can be very low, meaning that anti-latch-up protection must be applied, and potentially the frequency of latch-up might be too high for the application. This is a result of the CIS-120, which is a radar version detector, where we haven't seen any single event latch-up, nor SCU, up to 67.7 MeV, which is the limit at which we tested. Maybe can hold no latch-up or no SCU above this, but that's what's the limit of the test. And that can be done via, for the SCU, some design approach, as I mentioned, using the modeling from Muscat to design properly cells to be latch-up immune in first place, but also other approach like triple mode redundancy. For the latch-up, in order to minimize the gain within the thyristor of the latch-up loop, then some specific design rules are applied to minimize the possibility of this latch-up. Therefore, as a takeaway, AV-ion concern is mainly the digital sequencing and the readout periphery. There are 4 types of events: the single event transient, single event upset, and SEFI. The 3 are non-destructive but corrupt data, or can put the detector in an idle mode. The last one, single event latch-up, can't be destructive, and therefore care has to be taken. What we've demonstrated at Teledyne E2V is that it is possible to design for SET, SCU, and SEFI-free detector, meaning by that robust and radar. It is also possible to design, to lay out all our structure in a way that there is no latch-up up to at least 67.7 MeV. We also measured that the occurrence of latch-up reduces with low temperature. Therefore, at Teledyne E2V, we have developed design technique and layout design rules to mitigate for these possibilities and have detectors fully radared. During this AV-ion testing, ionization can create also RTS effects, but this is very negligible compared to total non-ionization dose RTS effects, and therefore are not considered as major there.